This is a classic momentum problem. Pause the video now. In fact, just in general, a good strategy on when you're looking at these videos is just feel forward, feel free to fast forward, rewind, pause. That's the whole point of having a tutorial video. You can go over it again and again. You can just jump to the end at the final answer and solution if you wish. And I see everything that happens in this classroom, so I see people that are going on their phones. It's not posted yet on YouTube, for those of you that might have been. So this collision is inelastic. This collision is inelastic, which means that the two cars are going to collide and stick together. In this case, it's two pass cars. And I'm going to use the law of conservation of momentum. And many people can state the law of conservation of momentum because you have a lot of practice stating the law of conservation of energy. And yes, you can say momentum cannot be created or destroyed. It can only be transferred from one object to another. I prefer to say that the total momentum before a collision is equal to the total momentum after the collision. Remember that momentum is a vector quantity. So if momentum, a momentum to the left will at least partially cancel out a momentum to the right. So I like to indicate it like this with total momentum 1 equals total momentum 2. And we're going to write that out. We're going to say we've got, what I like to do is, I'm going to get rid of these. Hold on, I guess I can't. What I like to do is just write out like all my MVs. So every time I know I have a momentum, it keeps doing that. Every time I know I have a momentum, I just write MV. So do the red part first and then do the blue subscripts later. So just write MV plus MV equals MV. Let me go through that. Moving object, right here, moving object. I have here a moving object. This represents, say, the 250 gram, and this represents the 500 gram, and this represents both of them stuck together. So throughout the whole before and after, I have 3 moving objects, okay? So everything on this side is before, and everything on this side is after. Then I go through and I put my subscripts in. This is sub A, sub A, sub B, sub B, sub T, sub F. Okay, so then the T stands for the total mass and the F stands for the final velocity because it doesn't really make sense to call it velocity A or velocity B because it's both. I've basically solved the problem now. Now I'm just going to plug my numbers in. Be careful of positives and negatives. Look at this. We got a -1 there, because it says it was moving at 1 meter per second to the left. +3. You don't have to put the positive in, obviously, but because it's to the right, you want to really understand that that's a positive quantity. There's my total mass, and my final velocity is not known. Notice I converted all of these to kilograms. Here's my final velocity, positive 0.33 meters per second, so this will be going to the right. That's not obvious. I mean, if you have something going left and something going right, you have to think about which has the greater momentum. Now change in kinetic energy. And those of you writing, like don't feel too rushed, even though I'm going a little bit fast, because this is all going to be on YouTube. You can hop on your phone, you can look at it. Change in kinetic energy, very simple. I'm going to calculate the kinetic energy before this collision occurred, and I'm going to calculate the kinetic energy after this collision occurred. So the kinetic energy before was the sum of 2 kinetic energies. Be careful. We are not adding up the masses and adding up the velocities and calculating kinetic energy once. Do each one individually. You may think it's mathematically the same, and it is not. You just do each one, calculate that kinetic energy of A, that kinetic energy of B. Is kinetic energy a scalar or a vector?
Scalar.
It's a scalar, so kinetic energy can only add up. Even though they're going in opposite directions, be careful. This is still a plus sign, and both of these are still going to be positive quantities. So those kinetic energies are not, can in no way diminish. If you have 2 moving objects, it's always going to be more kinetic energy than if you just had only one of those moving objects moving at the same speed. So now I'm just going to plug in the kinetic energy in the beginning was 1.375 joules. The kinetic energy at the end, I really only have one object, right? So the kinetic energy at the end was the total mass, 1/2 times total mass times the final velocity squared. You end up with 0.041 joules. This may seem weird, but if you think about what inelastic collisions are, it makes sense that some energy was lost, and in fact the change was negative 1.33. Why does it make sense to you guys that it should be a negative? It should be a loss of kinetic energy. There should be less kinetic energy at the end. Does that make sense to you? Because when we had this collision, this was the kind of collision where some deformation can occur, where some heat is generated due to friction, due to that deformation, sound is generated, vibrations are generated, all forms of energy that would tend to dissipate the kinetic energy. So what looks like a loss is just converted to other less usable forms. Okay, to summarize, I did use the law of conservation of energy. I used it right here by saying that the total momentum before equals the total momentum after. Pay attention to negative signs. Make sure if it's inelastic, you're thinking about the total mass, and then you can just consider it one object. Write out your MVs first and then put your subscripts in later. There was a moving object, and then another moving object, and then another moving object. Remember that for kinetic energy, you can't lose any kinetic energy, like they can't cancel out just because one's moving left and one's moving right, or one's moving north or one's moving south. And the change is the final minus the initial. So if you lose kinetic energy, it's going to be negative.